This really, truth be told, there is nothing new in today's lesson. You know all this stuff. We just got to put some of the things together that you know, just to make sure you're doing it right. Okay? So, we're going to be doing, hi Kylie, I've counted you absent, make sure I fix it. We're going to be doing hypotheses testing for means. Hypotheses testing for means. Okay? So, here we go. I'll jump right into the conditions. Of course, we're doing one sample today. Thursday, we'll be doing two sample. So those conditions are a little bit different, but these conditions are exactly the same as confidence intervals for means. We got to have the randomness, we got to have the 10%, and we have to have large counts. And the way we show large counts for means is the population is normal, which hardly ever happens. We want the sample size to be larger than 30, or we'll have to graph the data. On your test on the 26th, you will graph the data. It won't be over 30, and the population won't be known. One of the questions, you'll graph the data. One of the other ones, I'll tell you, will be over 30. Okay? One of your questions will be a confidence interval, and one of them will be a hypothesis test. One of them will be one sample, and one of them will be two samples. Okay with that? So that's two questions, free response on the next exam. Y'all okay with the conditions? We've won these conditions out. They're the same throughout the entire semester. The one that changes is the large counts. All right, n times p hat, n times p hat 1. There's a bunch of those. Here it's just 30. You're lucky. They're the same for means no matter what. Okay? All right, no pencils, y'all good. Click. If you have to graph it, let me rephrase that. When you have to graph it, you have to put that graph on your paper. Just a sketch. You're not expected to get a ruler out and make it gorgeous, but you are expected to graph that on your paper. I hate this. I love this laser, but it doesn't work up here. Okay. Hypotheses. Remember, hypotheses testing or significance test have hypotheses. So we're going to change it ever so slightly from proportions, and we're just going to say mu equals, right? Mu equals for the ho, mu equals. And then, of course, ha, mu is less than, mu is greater than, or mu is not equal to. Okay? So mu this time, not p. P for proportions, mu for means. And the most important thing, or let me rephrase that, it's not the most important thing, but one of the things that many of you guys forgot to do on the last test is to define mu in words. Tell me what mu is in words. Mu is the true mean. True mean of yada, 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 yada. Make sure you put it in words. That was subtracted quite a few on exams. A lot of people got the ho, a lot of people got the ha, just didn't tell me what the p was in words. You have to put it in words. You have to put it in words. Okay? Yippee, yippee, yo. Click, click. Psh, 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 psh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Smallest amount I think I've ever taught. I had a class of 6 one year. Make sure mu references the population, not the sample. That's what true mean. All Okay, don't forget that. Don't forget that. Remember that when it's a greater than, that's a right tail test or a, what do they call it, upper tail test. Upper tail test when it's greater than. When it's less than, it's a left tailed or a lower tailed. And then not equals to, of course, it's a two tailed or both tails or left and right tails. Okay, don't forget that. We learned that in chapter 9. Okay. Just like last chapter, and all means, we don't know the population standard deviation. So because we don't know that, we're using T's as our critical values. T's go with means. Z's go with proportions. If it's proportional data, you're using Z's. Normal CDS, inverse norms, whatever we got to do. If it's means, we're using T's. TCDS, inverse T's. Always, always, always. Formula, dadgummit, I hit it. Formula, that's the words. It's your job to turn those words into variables. It's your job to turn those words into variables. So your test statistic is T. Your test statistic is T. Your statistic is X bar. Your parameter is mu. And if you have to, you can put the ho, right? That's the claim. And then your standard deviation or standard error of the statistic is S of X over the square root of N. You would love to be able to put sigma right there, but we don't know what it is. We don't know that population average. We know what the claim of mu is, but we still don't know what the population of sigma is, which is why we have to use T's. That's why we have to use T's. If by some crazy chance I knew what sigma was, then that would change that to a Z. If. So that's the formula to find the T. Of course, we've learned about it. We don't really write this down on our notes if it's a free response. However, that's like multiple choice type stuff. And a big thing, here's a big hint, guys, on the multiple choice, they like to put DF down there. That's one of the things that they're going to try to trick you with, okay? So if your sample size is 37, they'll put 36 down there as the DF. So just make sure you know that that is the N value. Go ahead, Ev, whenever you. Okay, so make sure. Make sure. Probably check out through the North office. Or, yeah. Okay, click. There is non-hieroglyphics. Beautiful, beautiful. DF is simply N minus 1. It's N minus 1, just like it was in chapter 9 or 10. What are we in? We're in 10 now. Chapter 9. Okay, it's N minus 1. It's not a bad formula. When it becomes 2 sample, it's the bad formula, but the calculator still gives it to you. So your degrees of freedom is N minus 1. And so this, I mean, you know this, but I do need to make sure you teach this part of it, right? We're not talking normal distributions. We're not talking Z distributions. We're talking T distributions. And so we're going to use T CDF, not normal CDF. T CDF, not normal CDF. It always goes your lower bound, your upper bound, and then your degrees of freedom. Of course, it still tells you this, right? Left bound, upper bound, and DF. Okay? So just to make sure you guys are aware, here we go. Calculator, right? Distributions, second distributions. Go there. There they are. That's normal PDF we'll never ever use. There's normal CDF. And there's inverse norm. So those are the two we use for Z's. Inverse T, T PDF you'll never use, and then there's T CDF. So those are the two we're using for means. Those are for next chapter. Okay? Beautiful. Beautiful. Click. There's lifetime hours of the 15 deluxe AAA batteries from a company's random sample. Check if the conditions are met. Very similar to something you're going to see on the test. So SRS, pencil. SRS 15 deluxe batteries. 15 is less than 10% of all batteries. You almost have to write it like this. Don't say 10%, check. That won't do it. 15 less than 10% of all. This is not big enough. I don't know what the population looks like, so I have to graph it. And this is what you'll have to do on your test. So make sure you guys know how to do that. You can do it in Desmos, or you can do it with the calculator. Stat edit. There's the calculator, there's the battery data. Okay, so what's in there? I got it in mine already. There's the calculator battery. Boom, boom. Second y equals. Graph it, turn it on, do the modified box plot. That one says L2. I don't want L2, I want L1. Shift L1, shift 1, shift 2, shift 3. Okay, graph, probably won't see it. Zoom 9. Zoom 9. There it is, beautiful. Just sketch that on your paper. Sketch it. Those look almost exactly the same. This might be a little bit longer, and that shifted a little bit to the left. So just sketch it on your paper. Just sketch it on your paper. If you get really worried about it and you for sure you know you want your points, hit trace. That's 33. That's 44. That's 51. And you can label that if you wanted to. Not required. That's 27. And then that's 17. Doesn't take a whole lot of time to write those numbers down if you're worried about not getting the points for it. Pretty much the only way you're not going to get the points is not do it. Any question about those conditions? Y'all good? Happy, happy? 3 points on the test at least? At least. Click. SRS 15 deluxe batteries. 15 is less than 10% of all. The box plot shows no strong skewness or outliers. And reference it. Don't say it without something I can look at. So just sketch it on your paper. Pencils are going. What questions you got? Nothing new, I hope. All we've talked about is the conditions, really. TCDF as opposed to normal CDF. That comes into play in just a second. Formula, T equals statistic, X bar, parameter. It's a lot of stuff you know from the previous chapter or 2 chapters ago. Okay, good. Click. Suppose I want to perform a test. Whoops. That's better if I write it. Mu equals 5. Mu does not equal 5. At the 0.01 significance, a random sample of 37 from the population gives me an X bar of 4.81. Assume the conditions are met. If they tell you that, guys, don't test them. If they tell you conditions have been met, don't test them. You don't have to test them. They're not going to look for it. I'll start doing that on some of your tests. because I've already tested if you know your conditions by quite a bit by now. Okay. Explain why the sample gives me some evidence. That gives me some evidence right there. I'm trying to show that it's not 5, and my sample gives me not 5. If my sample gave me 5, it's going to be impossible to reject that. Impossible to reject it if my sample is 5. If I'm looking for mu greater than 5, it's impossible for me to prove it. I'm just looking for different than 5, so that's 4.8. Good enough? Click, click. Calculate the standardized test statistic. X bar 4.81 minus mu over the standard deviation square root 37. That's the standardized test statistic, and then the p-value. Okay, let's go to our calculators or Desmos. Calculator, stat, test, and it's the second one, t test. T test. Not 2, it's not a z, it's just a t test. And we either have the data or we have the stats. Now we have the stats for this particular question. And they said mu is 5. And they said the standard deviation is not. It was 4 point, you got it? 4 point, what was it? 4.84? 81, thank you. With a standard deviation of 0.365. Whoops, thank you. 3 didn't go, did it? 365. 37. Okay, and we think it's not equal to. All right, we're going to let our calculator do all the work. Boom, calculate, boom. There's that t, negative 3.166. There's the p-value, 0.003. X bar is 4.81, standard deviation is 0.365, and n is 37. Negative 3.166. Negative 3.166. There it is. 0.166. If you had that t critical and you need to turn it to the p, that's how you do it. Okay, df is 36. We hit paste. Hold on, that's not the same p-value I got. Y'all remember? What tail test is this? It was a two-tailed because it was a not equals 2. So you had to double this. You have to double it because it was a two-tailed test. I only calculated 1. I went from negative 999 to negative 3. That only did the left-tailed. Got to double it. Calculator does it. So when I did stat test, right, and did the t test, and I did that, it doubled it for me. So I don't have to worry about doubling that. But if you do the TCDF and it's two-tailed, you have to double it. Okay, very good. Beautiful. Here's the t, negative 3.17. df is 36. P-value 0.0031. 0.0031. There it's showing it to you on your calculator if you needed it. You still have a 4-step process, guys. Method, calculations, conditions, conclusions. If you make that big plus sign, most students do it okay because they list everything they need most of the time. They may forget a little something here or there. Method 1, SAMP, mean T test. One sample, mean, T test. Don't put proportions. Don't put intervals. Don't put anything that makes it seem like it's not a test. It's not means. Okay, that's your method. Don't forget to put the ho and the ha, and don't forget to tell me what mu is. Don't forget to put these things. However many points you got to keep in your head to keep all this stuff. I kind of do rules of three. 1, 2, 3. 3 conditions. T value or T score, P value. I don't know from there. X bar, standard, yeah. Got to do a bunch of stuff. Method. Got to get that on there. Conditions, you know those, right? Random, 10%, large counts. You know those. We've got those down. I hope. Calculations, guys, all I do is make sure you have the name of the formula in there. Have the name or the formula. Don't care. One of those two has got to be there. Name or formula. I like the name better than the formula. You put the formula wrong, it's going to be counted wrong. Put the name or the formula. And then I just label everything. Whatever my calculator gives me, I put it down. I put X bar. I put standard deviation of X. I put N. I'll put DF. I'll put alpha. What else? P-value, T-score, mu, whatever I can put down, I like to put down for the calculations. Whatever I can put down. What if I leave something off? Don't. Bless you. What if I put extra? I don't know what you could possibly put extra. The calculations has gotten really lackadaisical on its grading. I just need to see what you did or what you got down there, what values you used. They for sure want to see the T-score and the P-value. They for sure want to see those. Those are like have-tos. Got to see those. The rest of that stuff you need to see. And then your conclusion, which you guys already know. If P is less, we reject. Less, reject, there is enough evidence. If it's greater than you fail to reject, then there's not enough evidence. Big words go together, little words go together. Less, reject, is. Greater, fail to reject, is not. Make your decision about ho. Make your conclusion about ha. Reject or fail to reject. There is enough evidence or not enough evidence. And then, of course, put it in context. Put it in context. Yes, no, maybe. Almost getting boring. Hope. Hopefully by now we're starting to get this. Does the data provide convincing evidence? That means you got to do the full-blown deal. Does it provide convincing evidence? I got 15 randomly chosen locations. Random. 15 is less than 10% of all locations. And then I got to graph that data. So let's go. Let's look at it. It's already in my calculator. Second y equals, enter. It's in L2. L2. When I graph it, I won't see it because my window's jacked up. Zoom 9. There it is. Gorgeous. It's not strongly skewed. There's no outliers. It's not strongly skewed. There's no outliers. We'll put that on our paper and we'll go to town. Everybody okay with the calculator? Anything about the calculator? Desmos will do it too. All right, Ho. An average dissolved OG below 5 puts everything at risk. Ho, mu equals 5. When it's below 5, that's where we got issues. And make sure you tell me what mu is. Mu mu is the true mean DO level. Mu is the true mean DO level. Forgot the pencil. Is true mean DO level. I mean, make sure you guys know how to do this on your calculator too. And then we'll go to the test. Stat, test, t-test, and use the data this time. Data. There's your Ho. Data comes from L2. Frequency is 1. Not equal to. I don't want not equal to. I want less than. Less than. And so we'll just calculate. Bam. There it gives you the T credit or the T score. There's the p-value. There's X bar. You get that from your data. There's the standard deviation. That's important to know just in case you input the data wrong. If you input the data wrong, then your X bar is going to be different. And if your X bar is different, we know you put your data in wrong. There's N. It doesn't give you DF. DF equals 14. Put that down. It didn't give you alpha. I think alpha was 0.01. I don't think it matters what alpha is because P is going to be greater than all of them. Conclusion. Since p-value is greater than alpha, we fail to reject. There's not enough evidence to say that the DO level is below aquatic life. Here's where I'm going to get it from, guys. Just come on. Since my p-value was high, I fail to reject this. There's not enough evidence to say that the DO level is, the aquatic level is at risk. There's not enough evidence to suggest the aquatic level is at risk. There's not enough evidence to suggest the mean DO level is below 5. Yes, no, maybe? Good? Easy peasy. I hope. I hope. I hope you're almost bored of this. That means you got it. There's a condition. There's my Ho and Haas. There's my conditions. There's my normality. That's all conditions. There's X bar. There's the standard deviation. There's the T score. There's the DF. Here's the P value. Because the P value of 0.18 is greater than 0.05, we fail to reject. We don't have enough evidence that the true mean is less than 5. Don't be sorry. You're okay. She's not. She's not. Thank you. You're fine. Scared me. Given your conclusion, what type of error could we made? We did reject or failed to reject? We failed to reject. So we could have made a type 2. If we could have made a type 2, that means we did not have enough evidence for Ha, and we should have. That means what? The aquatic life is at risk. The aquatic life is at risk, and we came up with the conclusion that it was not. Yay? Man, y'all are a lively bunch today. Because we failed to reject, we could have made a type 2. If we did, then the true mean level in the stream is less than 5. And we didn't find that information. That would imply aquatic life is at risk, and we said everything's fine. That's a bad error. That's a bad error. There is a link between two-sided tests and confidence intervals. Don't forget this, okay? They're going to really start linking this together a little bit more. They'll do it in your homework, right? If you're doing a 95% confidence interval, that puts alpha at 0.05. It's important to know that what level you are rejecting it at. If we did a 95% confidence interval, we're rejecting it at 0.05. If HO is not in the interval, you reject. If it is in the interval, you cannot reject. That's a plausible value. We expect to see that. If it's not in there, we don't expect to see it. It's not plausible, we will reject. Hawaii Pineapple Company, the mean weight of a large field was 31. Whoops, sorry. We're almost done. Bear with me. The mean weight is 31. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect. We don't know if it's going to be higher. We don't know if it's going to be lower. We just wonder if it affects it. To find out, they weigh a random sample of 50. State the appropriate pair of hypotheses. I already did. I did not say mu is the true mean weight of pineapples. Good enough. Click. Beautiful. Click. Check the conditions. We got a random sample of pineapples. N is equal to 50, which is greater than 30. And 50 is less than 10% of all. Those are easy ones to check. Don't have to do much of anything. A 95% confidence interval put it at 31.255 to 32.61. Based on this interval, what conclusion can you make? Since 31 is not in my interval, it's not plausible, therefore we will reject. Now, be careful here. Well, some students will say this. We have enough evidence to say that the mean weight is greater than. Don't say that. Because we didn't say that. We tried to prove that it was different than 31. And so that's what we can say is we reject this. We have enough evidence to suggest it is different, even though it really looks like it's greater. We didn't do a right-tailed test. We did a two-tailed test. And if you do a two-tailed test, we can't say higher or lower. All we can say is different. All we can say is different. Beautiful. Can we conclude that the different irrigation system caused it? And the answer is no, because we did not do a cause and effect. Clicky, click, click. Beautiful. I hope, guys, you can state and check the conditions. I hope that you can calculate the standardized test statistic as well as the p-value. And I hope that you can perform a significance test about the population mean. I really hope you can use a confidence interval to make a conclusion on a two-sided test. What do you think? Yes, no, maybe? Almost boring. Homework's posted. Homework's posted. Thursday, we will do two sample Again, not a whole lot to be shown here. There is matched pairs. There is matched pairs. So we need to make sure we emphasize that part of it. Other than that, we should be pretty good on Thursday. We will review Tuesday, and we're going to test the next Thursday. Yippee, yippee, yo.